Okay, so this evening we want to look at this topic of work, energy, and power. So we hope to look at what we mean by work in physics, and also possibly, if we make good progress, what forms of energy we're interested in. Then also there's something called power. Also in our discussion, we'll look at some important relationships, and of importance to us is something called the work energy theorem, which gives us the connection between work and energy. And there's also something called the principle of conservation of energy. So that's what I think by tomorrow we'll be able to finish looking at this bit. Okay. So by the time we're done with this, you should be able to define what work is, and also you should also be able to calculate the work in a number of situations. Then the other thing is there's a form of energy which you'll be interested in called kinetic energy. You should be able to work out the kinetic energy using this expression. We'll not come up with it, we're just going to use it. Then there's also another form of energy called gravitational potential energy. So this is basically the energy a body has as a result of its height from the surface of the earth. So you should also be able to work that out. Then we're going to use the fact that you can change from different forms of energy. You can move between different forms of energy through the principle of conservation of energy. So as you change from one form of energy to another, you are actually not creating anything new, or neither are you destroying, but the energy is simply changing forms or phases. Last but not least, there is something called power. So we'll see how to work out the power. This is most likely going to be tomorrow. In terms of the work done divided by the time it has taken to do the said work, and also we'll come up with another relationship of power, which is this: power is equal to the force multiplied by the average velocity v. So we'll see how we can use these expressions. For starters, in a nutshell, when you perform work, when you do work, and this work is actually done on another object, so what actually happens is that you end up transferring energy. So the object you're performing work on will gain some energy. So in a nutshell, work is a way of transferring energy from one body to another. So if you are pushing a body, or you are pulling an object, and this object moves through a particular distance, then work has been done, because that object moving has got a certain amount of energy associated with that. So that is what we are interested in. Now, of course, this particular object is going to move in a particular direction, which is the displacement, and you can apply your force in any particular direction also. What we are interested in is the part of the force which lies along the same direction as the direction in which the object is moving. So that bit of the force which lies in the same direction as the direction in which the object is moving, that is a part of the force we are interested in, and that's what we are referring to as the x component of the force, the component of the force which lies along the direction of the displacement. So if your force was pointing in a particular direction, then as a result of this force, you apply this force, either you're pulling or you push an object, and an object moves in a particular direction. The work done, or the energy you have transferred as a result of this process, is equals to the component of the force in the same direction as the displacement, which is our fx, multiplied by the displacement, or the distance which the object moves. This fx is just the x component of the force, and we know how to work out an x component of a force. It's just, in this case, it's just the f multiplied by cos theta. So in this case, when you do that, you're going to have f cos theta multiplied by the displacement. So we end up having the work done being equals to the force, the displacement, and the product of the cosine of the angle between the direction in which the force is pointing, and the displacement in which the object is moving. So this is how we define work. Work is defined as a product of force, displacement, then there's a small bit which is called the cosine of the angle between the force and the displacement. So the F is the force you apply on an object. So whether you're pulling this particular object or you're pushing it, it does not really matter, but it's an external force. The displacement S is the straight line distance in which the object moves as a result of this particular force, and the theta is the angle between the force and the direction in which the displacement moves. Are we clear on what work is? Okay. Next, force is not a vector. Force is actually work is not a vector. Work is actually a scalar. As much as we are multiplying the force, which is a vector, times the displacement, which is a vector, when you multiply vectors, then after that you multiply by the cosine of the angle between these vectors, what you get is actually a scalar quantity. So you get a quantity which only has got size but has got no direction. So work is one of those physical quantities which is a scalar. Okay. The unit of work is the joule, and 1 joule is defined as the amount of energy which is going to be transferred when you have a force of 1 Newton causing an object to move through a distance of 1 meter. So the amount of energy which is going to be transferred to that particular object, if this force of 1 Newton and the displacement are in the same direction, then amount of energy transferred is what we are referring to as the joule. From this definition, you also notice that you cannot have work done, you cannot do work if the object doesn't move. So if you push an object or you're pulling an object, then despite you're trying to pull this object or push it, the object refuses to move. The displacement is equal to 0. So the object refuses to change its position. If the object refuses to change its position, then as you can see from this expression, you have whatever force you're applying, you're going to have a displacement of 0, then you're going to be multiplying by the cosine of the angle between the force and the displacement, which is of course is equal to 0. So when you multiply this whole thing, it will end up being 0. So the first thing to notice is that if you have a force, you apply a force, and this particular force, whether you're trying to push or pull, fails to change the position of an object, meaning that there is no displacement, then right there and then, if there is no displacement, it means that the work done is 0. So there is no work done if an object does not move. So your object has to move. It has to change its position for work to be done. So that's the first thing. You need an object's position to change. If the position of the object changes, then there is a chance that work could be done. It's not obvious that work is going to be done, but there is a good chance that actually work is going to be done. The other thing about work is that work also depends on these bits. It depends on the value of cos theta. And cos theta is the angle between the force you're applying on your objects and the direction in which the object is moving. So you can have different values of theta. For example, if the force and the displacement are in the same direction, so in that case your theta is going to be equal to 0. If your force and displacement are perpendicular to each other or 90 degrees, then your force and displacement will be 90 degrees. If your force and displacement are acting in opposite directions, then your theta is going to be equals to 180 degrees. So depending on how the force and the displacement are oriented or arranged with respect to each other, it will determine whether work can be done or not. In the case where the force you're pushing with the force or you're pulling with the force, and this force is in the same direction as the displacement. So if the force is in the same direction as the displacement in which the object is moving, so in that case, then the angle between the force and the displacement is equal to 0. So theta is equal to 0. So when theta is equal to 0, then you can work out the work in that case. So the work is going to be equal to the force, the displacement multiplied by the cosine of the angle, which is 0 degrees. So in this case, cos 0 degrees is just equals to 1. So you end up having work which is just given by the product of the force and the displacement. So in this case, work is just going to be equal to Fs. As you can see here, this work, as much as it is not a vector but a scalar, work in this case is positive. So this work has got a positive value. And what does it mean if the work is positive? It means that when you have a positive work, it means that energy is transferred to the object that is being moved through a particular distance. So the force you are applying on this particular object, causing the object to move through a particular distance, will result in the transfer of energy. So if you perform positive work, if the work you do is positive, then the object you're performing work on is going to gain energy. So the object you're performing work on is going to gain energy in that case. The other case is when your force you're applying on a particular object is at 90 degrees to the direction in which the object is moving. So if the force is at 90 degrees to the direction in which the object is moving, if such a case is possible, then in that case, here you have got your cos 90. The angle between the force and the displacement is going to be 90 degrees. And cos 90 is equal to 0. Since cos 90 is equal to 0, you work out the force, you try to calculate the work. So the work done is going to be equal to the force, whatever the force is, then the displacement, whatever the displacement is, but this bit here is going to give you a 0, and you end up having work done equals to 0. 0 work means that there is no energy being transferred by the force to this particular object. So if the force and the displacement are at 90 degrees, then there is no work done. So we are seeing here that it turns out that apart from having a requirement that there should be a non-zero displacement, so you should have a certain displacement. Apart from having a displacement, work is affected by the angle between the force and the displacement. So in this case, if the angle is 90 degrees, then there is no work done. You can also have a case where the force and the displacement are at 90 degrees to each other, like in the case with friction. Friction is always pointing in a direction which is opposite the direction in which the object is moving. So in that case, if the friction force is pointing backwards, then the object is moving forward, so the angle between the friction force and the displacement is going to be equal to 180 degrees. If theta is equal to 180 degrees, so in that case you can do the work. The work done is going to be equal to the friction force multiplied by the displacement times the cosine of 180 degrees, and this cosine of 180 degrees is going to give you a minus 1, which is going to end up giving you minus Fas. So in this case, you see that the work done is negative. So you can have negative work. Negative work means that in this case, because positive work, when you have positive work, the force you have applied on this particular object is transferring energy to this particular object. In this case, when you have negative work, there is no transfer of energy, but instead the energy is removed from this particular object. That is why if energy is removed from a particular object, you see the case where an object can slide to a stop. The reason why an object is sliding to a stop is because it is running out of energy. The reason why it's running out of energy is because there is this force, friction, which does work against the object, and it depletes the energy of this particular object until it comes to a stop. Okay, so that is about work. How you calculate the work, and of course, for you to calculate the work, you need to have a value of displacement which is not equal to 0. Apart from that, you also need to have an appropriate angle. An angle of 90 degrees is not going to help you perform any work. You have maximum work performed when the force and the displacement are pointing in the same direction, and you also have negative work being done if the force and the displacement, maximum negative work being done if the force and the displacement are opposite each other. Any questions on what work is and how we calculate work? The next bit, we are going to look at a few examples on how you actually work out this work. So in this case, example number 1, you have a force of 3 newtons acts through a distance of 12 meters in the same direction of the force. So we can see that this force of 3 newtons and the displacement 12 meters, they're in the same direction. So if they're in the same direction, then the angle between the force and the displacement should be equal to 0. So the work, W, is equal to the force multiplied by the displacement multiplied by the cosine of the angle between the force and the displacement. The angle is the same, the force and the displacement are in the same direction, therefore the angle between them is 0 degrees. So you end up having the work done being equals to the force, which is 3 newtons, times the displacement, which is 12 meters, multiplied by the cosine of the angle, 0 degrees, which is 36 joules. So that is how you work out the work if the force and the displacement are in the same direction. The angle between them is 0 degrees, so this cos 0 degrees is just 1. Like that. Example 2, an object is being pulled along the ground by a 75 Newton force directed at 28 degrees above the horizontal. How much work does the force do in pulling the object 8 meters? So again, we have a force, an external force which is pulling an object, that is 75 newtons, and of course the object gets this, as a result of this pull force, the object gets displaced 8 meters. The angle between this force and the displacement, we are told, which is along the horizontal, is 28 degrees. So in this case, we work out the work. W is equal to the force multiplied by the displacement multiplied by the cosine of the angle. So in this case, you have the force is 75 newtons, the displacement is 8 meters, and the cosine, the angle is 28 degrees. So we end up having 530 joules of work. As you can see, work is measured in joules. This is the amount of energy that will be transferred to the particular object in question, which is being moved around. So in the first case, it's just 36 joules of energy being transferred. In this other case, it is 530 joules of energy being transferred. Any questions so far? Do you have any questions so far? Okay, next. A 0.3 kg object slides 0.8 meters along the horizontal table. How much work is done overcoming friction between the objects and the table if the coefficient of friction is 0.2? So again, in this case, we are talking about friction and work. The friction is always pointing in the opposite direction. So friction points in a direction which is opposite the displacement. So our object slides 0.8 meters going forward, but the friction is going to be pointing in a direction which is opposite. And we know the mass of the object, and we also know the coefficient of friction. So for us to work out work, we need to find the force, which is the friction force. Then after that, we multiply our force times the displacement, multiplied by the cosine of the angle, which is in this case 180 degrees. So the force we are looking for is the friction force, and you can always find friction force using this expression. The friction force is equal to the coefficient of kinetic friction multiplied by the normal force. The coefficient of kinetic friction in this case is 0.2, and the normal force we can get from the weight, from the mass of the object multiplied by g. So the normal force Fn is equal to the mass of the object multiplied by acceleration due to gravity, so that's mg. So the normal force is equal to 0.3 kg times 9.8 meters per second, and this gives you a normal force of 2.94. Remember that a normal force is the reaction or the push of the surface on which this particular object is sliding. This object with a mass of 0.3 has got a certain amount of weight, okay, and this surface is not happy about that there's this amount of weight being exerted on it, so it pushes back, and that's how we get the normal force on a flat surface. So on a flat surface, the normal force is just the mass multiplied by the acceleration due to gravity. So now that we have got the normal force being equal to this, we can find the friction force by multiplying the coefficient of kinetic friction and our normal force. So in this case, the friction force is equal to the coefficient of kinetic friction multiplied by the normal force, and we get a friction force which is equal to 0.588 newtons. So that is our friction force. This friction force of 0.588 newtons is acting in a direction which is opposite the direction in which the object is sliding. So the angle between our friction force and the displacement is 180 degrees. So in that case, we can work out the work to be equal to the friction force multiplied by the displacement times the cosine of the angle. The displacement, we are told our object comes to a stop in 0.8 meters. So that's our displacement. So it's going to be the friction force, which is 0.588 newtons, times the displacement, which is 0.8, times the cosine of 180 degrees, and this cosine of 180 degrees is going to give us a negative, so we end up having work done being equals to minus 0.47 joules. So you can see that whenever friction is doing work, the work done by friction is always negative. The reason why it's negative is because friction takes away energy from any particular object. That's why an object will come to a stop when it is sliding on a flat surface, or especially on a flat surface. Whenever an object is sliding on a flat surface, it will come to a stop because friction does work against that particular object. Any question? Do you have any questions so far? Yes, go ahead. On the what?
On the friction. Negative.
What about friction?
On that statement, because I think it is negative.
Why it's negative? The reason why it's negative is because of this. Cosine of 180 degrees is negative 1. So if you work out cosine and 180 degrees, you're going to get a negative 1. So when you multiply by this, your work done comes out negative like this. This negative work means that energy is going to be taken away from the object. Okay. Is there another question? Or does that answer the question?
Yes, sir. Thank you.
Okay. Any other question? Okay. Next, example number 4. How much work is done against gravity in lifting a 3 kg object at constant velocity through a distance of 0.4? So there are two ways to approach things. The first thing to notice is that we are lifting this particular object at constant velocity. Therefore, there is no acceleration. If there is no acceleration, it means that the resultant force is equal to 0. So when you lift an object up, you have to pull this particular object you're lifting. So there's a lift force. However, this particular object has got a mass 3 kg, therefore this particular object has got weight. So you are lifting an object which has got weight, and the weight of this particular object is pointing down. That's where the weight is pointing. So the weight is pointing down, and you're lifting this particular object. Since you're lifting this particular object at constant velocity, it turns out that your resultant force, in this case, which is going to be the lift force minus the weight, is just going to be equal to 0. So in that case, if the resultant force is equal to 0, so you end up having the lift force being equal to the weight of the object, which is going to be equal to mg. So the size of the lift force is just going to be mg. So in that case, if the lift force is equal to mg, then you can work out how much the lift force is. It's going to be 3 kg times 9.8 meters per second squared, and you get a lift force which is equal to 29.4 newtons. So your lift force is pointing up. When you lift something, that particular something you're lifting also comes up. So in that case, your displacement and the lift force are in the same direction. So you end up having, so you can work out the work done, and you're lifting the object through a distance of 0.4 meters. So you end up having the work done being equals to the lift times the displacement multiplied by cosine of the angle. In this case, the lift force and the displacement are in the same direction, so you end up having your lift force is 29.4. The height through which you lift this particular object is 0.4 meters, and they are in the same direction, so you end up having work done being equals to 29.4 meters times 0.4 meters times the cosine of 0 degrees. You end up having the work done as 11.8 joules. So, what does this tell you? When you lift an object through a particular distance, that particular object you're lifting gains energy because you're doing positive work on that particular object. Are we clear? You lift the object using a force, an upward force. This object is going to move through a particular height in the same direction as the force. Therefore, the angle between the lift force and the direction in which the object is rising is the same. So the work which you get in this particular case turns out to be positive. So when you lift an object, that particular object gains a form of energy. At the moment, we are just saying that when the work done is positive, the object gains energy. When the work done is negative, the object is losing energy. What kind of energy is losing? What kind of energy is gaining? We are not saying that for now. But of course, as you can see, our next bit is energy. And when it comes to the subject of energy, basically life as we know it on Earth is not possible without energy. And the energy which we use on Earth comes from the sun. So every day the sun, we see the sun in our sky, and it provides us it provides our planet the energy which we need to live.
Sir, question.
Yes?
The previous examples I have used the angle was 0. Is it 90 degrees since we are lifting it up?
You're lifting something up. So when you lift something up, what happens? What direction does that particular something go? In which direction does it go? Sorry?
Y-axis.
Yeah, it goes in the y-axis, yes. So you're lifting something along the y-axis. That's where your force is, and that particular object goes along the y-axis. So the lift force and the displacement are in the same direction.
Now the angle is it 0 degrees or 90?
It is 0 because they are in the same direction. We are saying that if the force and the displacement are in the same direction, then the angle between them is 0 degrees. We don't measure this angle from the x-axis, no. This angle is the angle between the direction in which the object is moving and the direction in which the force is acting. Are we clear? You're trying to measure this angle from the x-axis. That's not what you're doing. This angle theta is the angle between the displacement and the lift and the force. You're pulling an object up, that particular object comes up. This pull force is a vector. The displacement, the height through which the particular object goes, is a vector. So the angle between them is 0 degrees because they are parallel or they're in the same direction. Are we clear? Is it clear? Okay, if there's no other question. Okay, so we are saying that the energy we need to sustain life on Earth comes from the sun. And how do we eventually get access to this energy? Well, some of this energy in the form of solar radiation or solar energy is absorbed by the clouds, it's absorbed by the oceans, and it's also absorbed by land. That's why our land is warm, and if you get into the water, you find that the water is also warm. Okay. Apart from that, there are other life forms, for example, plants and algae, which contain a chemical code, a chemical compound called chloroplast. Using this chloroplast, these plants and algae, they capture this energy and they change it into other forms. For example, carbohydrates, proteins and fats through a process called photosynthesis. So when you eat whatever carbohydrates, for example, in Zambia we like eating shima a lot, and of course there's protein, maybe milk and fats. When you eat these things, when you eat these carbohydrates or these proteins or these fats, which are chemical compounds, okay, one of the things you're trying to get as you're eating these carbohydrates and proteins and fats is you're trying to have access to energy. If you have a particular food, you buy a certain amount, a food product, processed food, let's say it's milk or whatever it is, maybe it's pasta. If you look at the package at the back, one of the key nutritional information which is there is the amount of energy you are going to get from that food. So the reason why we eat food, part of the reason why we eat food is because we want to get the energy which has been stored in this food when the plants captured this energy through photosynthesis. And that energy which has been stored in the food is what is called chemical energy. So this is what you're looking for. That's one thing. The other thing is, of course, you're looking for nutrients, maybe vitamins and these other things. But energy is a very, very important thing. That's why we spend, if you can afford it, if you've got the money to do that, you have breakfast, you have lunch, you have got supper, because you are trying to have access to this energy stored in the food. This chemical energy is what you need to stay alive, because you need it to keep your body temperature where it is. You also need it for doing other activities like breathing, movements, and all the other things you need to do. In the case of you students, you also need to study, but you might have noticed that just by sitting in a chair and you're trying to study, you are going to get hungry, because studying and keeping information in your head requires energy. If you are studying on an empty stomach, most likely your understanding or your retention of the information is not going to happen. So if you want to study and you want to understand properly, I would advise you to study and to try to study after you have eaten. Eat something first, not too much so that you fall asleep, but you have to eat something, because storing information in your head, making your head retain information, needs energy. Without energy, you will study but you forget. And moreover, there's the usual disturbances which happen when your body doesn't have enough energy and your body is telling you that you are hungry. So it starts making all these sounds telling you that we need food. Okay. However, the energy which is stored in food is not the reason why we are looking at this topic. There are forms of energy which are of interest to us, and that one form of energy which is of interest to us is the energy which a body has as a result of its motion. So if you've got an object of mass m, and this particular object of mass m is moving with the speed of velocity v, then it has got a form of energy called kinetic energy. This kinetic energy in a straight line, called translational kinetic energy in a straight line, Ke is equal to half mv squared. So when you move, you have a certain form of energy. And if you are moving around, you ate your breakfast, then you start moving around, the chemical energy is going to get used up. It will be converted, some of your chemical energy will be converted into this kinetic energy, and you spend it. So an object which is in motion has got a form of energy associated with it called kinetic energy, and this is how you work out the kinetic energy. The other form of energy we are interested in is a form of energy which is associated with the height above the ground. So if you are at a particular height above the ground, then there is going to be a form of energy you're going to have, and that is what we call gravitational potential energy. Gravitational potential energy is purely based on how high you are above the ground, and it's given by this. GPE is given by the mass multiplied by G times H. This mg, as you can see, mg is the weight of an object multiplied by the height of that particular object. So these are the two forms of energy we are going to be interested in this course. Later on, there is another form of energy called thermal energy. We'll look at that later, but for now, we are only introducing you to these three types of energy. There is chemical energy, and of particular interest in this course, there is kinetic energy and also gravitational potential energy. Any questions on these forms of energy? Do we have any questions? So if you are at a particular height, then you've got a form of energy associated with height called gravitational potential energy. If you are moving with a particular velocity, then you have a form of energy called kinetic energy. Okay? Example 5. A 0.2 kg mass falls through a distance of 4 meters. How much work is done on it by gravitational force? And B, how much gravitational potential energy did it lose? So if an object is going to fall through 4 meters, so it's falling down by 4 meters, it is being pulled by gravity. So the object is falling down, so it's coming down, and gravity is pointing down. The weight, the gravitational force you're talking about here is the weight of the object. So the weight of the object is pointing down, and the object is falling down. So as you can see here, the gravity, the weight, and the displacement are in the same direction. So if you want to find out how much work has been done, we need to work out what the weight is, then later on multiply the weight times this height through which the particular object falls through, and the angle between them, which is 0 degrees. So the weight of the object, which is a gravitational force, is going to be equal to the mass of the object times g, and that weight of the object is going to be 0.2 kgs times 9.8 meters per second squared. So you're going to get a weight which is equal to 19.6 newtons. With this weight of 19.6 newtons, the weight always points down. This particular object is falling through a height, falls through a distance of 4 meters, so the displacement is also down, so the angle between these is 0 degrees. So in that case, we end up having weight equals to work done equals to the weight times the 0.04 meters multiplied by the cosine of the displacement, which is that. So the work done is equals to the weight, which is 19.6, multiplied by the 4 meters times the cosine of the angle, which is 0 degrees, cos 0 degrees, which is 1, and you end up having the work done being equals to 78.4 joules. So this is how much work gravity does. So when gravity is pulling this particular object down, gravity is giving this object energy. So as an object is being pulled down, it's being given a form of energy because it's moving. It's being given kinetic energy. This object is moving as it's being pulled down. But as this object is being pulled down, from the definition of gravitational potential energy, you know that there is energy associated with height. So this particular object is losing height. And in that case, the lost gravitational potential energy is just going to be equal to the weight of the object multiplied by the height through which this particular object falls through, which is GPE is equal to the mass, the acceleration to gravity, and the height. And if you do this, you work out this gravitational potential energy is equals to 2 kgs times 9.8 meters per second squared times the height through which the object falls. So the gravitational potential energy which is going to be lost is going to be equals to 78.4 joules. So the lost gravitational potential energy and the work done, you can see the value is the same. This is why we have been saying that when you perform work, you are either transferring energy or you're removing energy from a particular object. In this case, when gravity does work, when gravity is pulling an object down, yes, it's giving that particular object a form of energy, this much, specifically kinetic energy. But at the same time, this particular object, because it's losing height, it's losing a form of energy which is gravitational potential energy. Okay, so today we're going to stop here. When we meet tomorrow, we're going to continue with this subject of energy and work, and we're going to make a connection between energy and work through this thing called the work energy theorem. So this work energy theorem is going to solidify the connection between the work done on an object and how much energy this particular object is going to gain, or how much energy this particular object is going to lose as a result of the work. If the work is positive, then this particular object will gain positive energy. If the work is negative, then this particular object, of course, is going to lose energy. Any questions? We stop here today. Questions? Okay, so if there are no questions, I'll stop sharing. See you tomorrow. And of course, the recorded video